1.3 again. We're going to finish it off, except it's going to all be trig limits. He started today's lesson with properties of limits, and he burned through it pretty quick, so I'm just going to talk quickly about them. I go over them a little bit. So the first property of limits is if you have a constant, so we're calling b here a constant, some number, it doesn't matter what it is, you can pull that number outside of the limit. So for example, if I have the limit as x goes to 2 of 3x squared, that is the same as the limit as x goes to 2, or 3 times the limit as x goes to 2 of x squared. Which you would plug in, you'd get 4, so the answer would be 12. Okay, so you can pull constants inside and outside of limits. You can also break up limits that have addition and subtraction in them to those individuals. So they write that as limit of f of x plus or minus g of x is equal to the limit of f of x as x goes to c plus or minus the limit of g of x as x goes to c. For example, most of the time you don't do this, only in specific cases. But if I have x going to 1 of 4x squared plus 2x, I can rewrite that as the limit as x goes to 1, 4x squared plus the limit as x goes to 1 of 2x, which is going to give me 4 plus 2, which is 6. And there you go. All right, now you wouldn't do it for a polynomial function. A lot of these things come into play when you're dealing with more complex functions, such as the trig stuff that we're going to look at today. Again, if you're multiplying, it's the same thing. You can break it up into the separate limits. So if I have x goes to 1, I'll just use a nice easy function. Something like that. I can rewrite it as the limit as x goes to 1 of x plus 1 times the limit as x goes to 1 of x plus 2. All right, which would be 2 times 3, which is 6. There you go. And then finally, division, same thing. I'm not going to, well, I guess I'll do an example. The limit as x goes to 1 of, I don't know, x plus 1 over 2x plus 1. That's equal to the limit as x goes to 1 of x plus 1 divided by the limit as x goes to 1 of 2x plus 1, which would be 2 over 3. There you go. All right, and the final one has to do with a power, whether it's a fractional power or an integer. So if the function is raised to a power, you can ignore the power, just find the limit of that function, and then raise your answer to the power. So if I have the limit as x goes to 1 of x plus 1 all squared, I can rewrite that as the limit as x goes to 1 of just x plus 1, and the whole thing is squared, which is going to give me 4. Okay. Now again, like I said, you wouldn't do it for polynomial functions because they're pretty straightforward. They're continuous. You can just plug it in and you get the answer, but they come into play when you're dealing with more complex functions. To practice what we just did here, page 67, number 37 and 39, those will give you practice with those different functions. And then when you come back, we are going to do trig limits. All right, everybody. So, trig limits. Now, if you have a trig function that is defined at the point that you're going to, just like any other function, you can solve the limit as we normally do. So, for example, if I say the limit as x goes to 0 of tan x. Now, tan does have undefined points. It's got those asymptotes at 90, 270, etc. Excuse me. But at 0, tan is defined. So I can literally just plug in 0 into tan. Tan of 0 is 0. And that's your answer. So if you, like we did before, if you can plug it in, plug it in. Another one, if I have x going to pi of x cos x, well, is cosine undefined anywhere? No. Is x undefined anywhere? No. So this is a completely continuous function. I can plug in my pi value and I get pi times cos of pi. What is cos of pi? If you don't remember your cosine graphs, which by what happened in class today when he asked you guys, you don't. Negative pi has a value of, pi has a value of -1 because it's right there. So I get pi times -1, which is just negative pi. All right, so if you can plug it in, you plug it in. The reality is a lot of trig functions you cannot plug in because they are undefined at certain points. So there's two special trig limits that you need to remember. I'll just call them special trig. Let's call them trig limits. Special trig limits. He showed you sort of a hand-waving proof in class today. You just need to remember them. You don't need to know the proof. If you want, you can look up the proof online. There's a bunch. There's a geometric proof of the sine one. Once you know the sine one, you can kind of get the other one using some manipulation. So the limit as x goes to 0, sine x over x is equal to 1. That's the first one, and the one that we use a lot. And the other one, limit as x goes to 0 of 1 minus cos x over x is equal to 0. Like I said, you don't need to know the proofs. He showed them to you in class. I can point you in a direction if you want to see a proof, but it's beyond the scope of this course. Okay, so having known those two limits, your goal when you're dealing with a trig function limit that is undefined at the point you're approaching is to make it look like one of those limits. So in a sense, it's like Math 12 proofs. You're going to have to use your Pythagorean identities and your basic trig function identities. So if you are, well, a lot of stuff open. Remember your Math 12. Here's the formula sheet. These ones here, cosecant 1 over sine, secant 1 over cosine, cotan is 1 over tan, tan is sine over cos, gets used a lot, cotan is cos over sine, gets used a lot. And the Pythagorean ones, these guys right here, really it's just sine squared plus cos squared is equal to 1 that we use the most of the time. The other ones might show up, but you don't need to worry for this class about any of the addition identities or the double angle identities. Those would be rare if they ever showed up. It's most Math 100, it's going to be, and Calculus 12, it's going to be just the basic primary identities, and sine squared plus cos squared is equal to 1. Okay, so here we go. Our first example. Call it A. The limit as x goes to 0 of tan x over x. Now clearly I can't plug in 0 because I'd end up with 0 over 0 because tan of 0 is 0, the bottom is 0, we get indeterminate form, the world blows up, and we're done. So there's got to be a way to manipulate this, and there is. From those identities, just like in Trig 2 in Math 12, you don't want tans, you want sines and cosines, because if you look at our identities, they're sines and cosines. So I have to get rid of the tan. Well, tan is sine over cosine. So I rewrite it as sine x over cos x all over x. And then we flip the denominator, which is x over 1, so we get, remember to write the limit every time. So I get that. So how does that help us? Well, hopefully you can see that is our identity up here. So I need to rewrite this. So now it becomes limit as x goes to 0, sine x over x times 1 over cos x. I didn't change anything. I just rewrote it into better grouping for us. And then using the properties of limits, which are up here, for multiplying, I can break it into two separate functions. So come back here, this now becomes the limit as x goes to 0, sine x over x times the limit as x goes to 0 of 1 over cos x. This is defined as being 1, so we know that. So that equals 1. This cosine, if you remember your cosine graph, or you can plug it in your calculator. That'll hurt me, but whatever. Cos of 0 has a value of 1. So that becomes 1. So the answer is 1 times 1, which is 1. All right, so the whole goal is to make it look like one of these two special trig ratios up here. Okay, next one. B. The limit as x goes to 0 of sine 4x over x. Okay, so it's the sine one. It looks very similar to what we have up here, except instead of just having an x in here, we've got this 4. The numerator, or the value of the x inside the trig function, sine, in this case, has to be the same as what's in the denominator. So I need to have a 4 in the denominator. So what we do is that's what I want, but I can't just put a 4 in the denominator. That's going to change things. But you can always multiply by 1. So that means I'm going to have 4 on the outside here, because really those 4s would cancel and would just give me back the original equation. Now, using our fact that we can pull constants out of a limit, I can then go pull this 4 out. And I get this. Now, this looks very similar to what we have up here, except we got these 4s. Now, I'm going to show you something. Check with Jean-Claude to see if he accepts this. But what you can do is you can say, okay, make a substitution. U is equal to 4x. Okay? So if u is equal to 4x and x is going to 0, what is u going to? Well, if I put 0 into there, u is going to 0 as well. So that means I can rewrite this limit as 4 times the limit as u goes to 0 of sine of u over u. Now, this is our identity up here. Okay? Doesn't matter what the variables are, as long as they're the same. So then I get 4 times 1, which is just 4. So some of you are going, why did we need to do that step? That's the mathematical reason why this works out. The shortcut is, once you get this, where you have what's inside the trig function, 4x, equaling what's in the denominator, that whole thing you can say is 1. Check with him on that, or do you have to show these steps? Okay, because every prof is different. I've had profs that say, once you get here, you're good, just go straight to 1. I've had other profs that say, no, you've got to show this substitution method. Okay, so just a heads up, and that's on you guys. All right. Let's see. Now, the limit as t goes to 3 of sine t minus 3 over t minus 3. Okay. So now I just said if these match, then you can just say it's 1. But the special case, our variable is going to 0. What's a variable going to here? It's going to 3. But if I plug in 3, I still get 0 in the denominator. So in this case, you're going to have to show the substitution for sure. Okay? So u is going to equal, I mean, you can choose any variable you want. I'm choosing u. U is going to be equal to the numerator, or what's in there. So that's going to sub both of those out. So if t is getting closer to 3, what is u getting closer to? It's going to be 0, right? Because if I put 3 in there, 3 minus 3 is 0. So now this limit becomes the limit as u goes to 0 of sine u over u. Well, that's our special identity, so we know the answer is 1. All right, 2 more to go, people. The limit as x goes to power of 4, 1 minus tan x sine x minus cos of x. Okay, so if you try to put in pi over 4, you're going to end up with 0 in the denominator. You can try it, and if you remember pi over 4, that is, waiting for somebody to answer, 45 degrees. The 45 degree special triangle is 1 root 2. So sine of pi over 4 would be 1 over root 2. So this, if you tried plugging it in, would be sine of pi over 4 can be opposite over hypotenuse, 1 over root 2, minus what's cosine? Oh, adjacent over that. It's 1 over root 2. So you end up with 0. So that's a gong show, a no-go. So we got to rewrite it. So just like trig 2, get rid of our tan. What is tan? Well, that is sine of x over cos of x over sine minus cos of x. Okay, just if you remember your trig 2, what you need to do for these types of questions, when you have something like this, you need to make a common denominator, which is going to be cos over cos. So you're going to get cos of x minus so the numerator becomes, just to clean it up, okay, we're going to flip the denominator, because really that's over 1. So then I get the limit as x goes to pi over 4 cos x minus sine of x over cos of x times 1 over sine x minus cos of x. Okay, now if you have, these two look like they want to cancel except they're in opposite directions or opposite signs. Factor a negative out of one of them, it doesn't matter which one. So I will do the numerator. If I take a negative out of here, that's going to flip all the signs. So I end up with sine of x minus cos of x. Then, surprise, surprise, those cancel. I'm left with the limit as x goes to pi over 4, negative 1 over cos of x. Cos of x is defined at pi over 4, and it's going to be negative 1 as I showed up there. Cos of pi over 4, 45 is 1 over root 2. So you get negative 1 over root 2, which is just negative root 2, or the decimal equivalent. All right, last one. E. What about this? Now, that looks like our identity, but it's flipped. Well, what if I do this? That's the exact same thing, right? Because a negative exponent means you flip it. And we learned from the power or the properties limits up here, if you have an exponent, you can take it out and use it on your final answer once you do the limit inside. Okay, so that is what we're going to do. I'm going to go the limit as x goes to 0 of sine x over x all to the negative 1. Well, the inside bit is our special identity, which is 1 to the negative 1. Negative exponent means you flip it, so that's 1 over 1, which is just 1. So you have another identity that you can choose to remember if you want. The limit as x goes to 0 of x over sine x is also equal to 1. All right, please practice those. We will practice those in class, but we're going to practice other stuff in class too tomorrow. I put these on the board, but just in case, page 67, 57, 63, oops, 73 odd, and 75 to 81 odd. All right, peoples, I'll see you tomorrow. Good luck.